Greetings everyone. We're going to be talking about inertial reference frames and center of mass. So here we have a picture of a mute swan flying over a nice quiet river. You can see that its neck is outstretched, but somehow it still remains balanced. So we're going to talk a little bit about this in the second half of this lecture, talking about center of mass. First, let's talk about reference frames. Until now, we've considered collisions where the observer is at rest. And then we considered what was happening in the collision. This car looks like it's moving at this speed, this car was at rest, and we ask, what happens after the collision? But our observer doesn't always have to be at rest. We could be observing this collision from inside the car. Then car 2 would look like it was the one at rest, and car 1 would look like it was approaching. If this doesn't quite make sense, what you can imagine is, let's stick car B and car A. Car A is waiting at some red light, car B is coming into the back. And now you're a stationary observer, you're standing at the sidewalk, you watch car B crash into car A. This example has you sitting in car B. And then car A is still stopped at the stoplight, but you are now in car B. So what you look like is that car B is not moving away from you, so its velocity is 0. But car A looks like it's now moving towards you. So these two are the same example. And what should be the case is that the laws of physics shouldn't change depending on where you observe what's going on here. It doesn't matter if you're a stationary observer or you're a moving observer, physics stays the same. So let's consider this case a little bit more in detail. So here we had what was going on in the collision. We had our initial velocity of car 2, car 1 was at rest. This is what we observed. Then there's some collision here, and then now after the collision, car 2 looks like it bounces back towards us, and car 1 moves away at some velocity. We measured these delta V's for each car, and we can find out all this information just by considering conservation of momentum. And since this is an elastic collision, we can consider how kinetic energy is conserved. So this is all we really need to know in order to solve what are these final velocities in this case. Now let's consider some moving reference frame. So instead of being at rest, we're now going to be moving to the left. This is a minus sign. To the left at 0.2. I think the way they drew this arrow is a little misleading, so we're going to draw it a different way. So now instead of going to the right, or being at rest, now we're moving to the left. And we're moving to the left at 0.2 meters per second. So originally car 2 in this rest frame is moving at 0.8 meters per second. But since now we're backing up at 0.2 meters per second, it now looks like it's at 0.8 plus this 0.2. So it looks like it's moving away from us at 1 meter per second. And the same thing has happened to this car. This car is at rest in the rest frame, but since we're moving backwards at 0.2, it now looks like it's moving at 0.2 away from us. So what does this mean for the collision? Well, the laws of physics stay the same, and we're going to work out what's going to happen in the following example. But what you're going to find out is that these delta V's stay the same. These delta V's are all about conservation of momentum. And if momentum is conserved in both these cases, then the laws of physics have not been violated just because we are in a different inertial reference frame. Alright, so here's our more in detailed example. And I'm going to draw each one out. So here's example 1. So here we have car A is driving north, so this is going to be our north direction. On Highway 34, heading out of town, and he's moving at 35 meters per second. Miles per hour, sorry. Car B is also driving north, but going a little slower, 30 miles per hour. Car C is somewhere up here, student C is somewhere up here, and they're at rest, just waiting to cross the street, hoping that these two guys will know they probably should slow down at this intersection. So then after a long enough time, car A, since it's moving faster than car B, it's eventually going to crash into the back of B. So let's answer a few of these questions first. So C, how fast does C observe A going? So C observes A going this 35 miles per hour north, and also observes B going 30 miles per hour north. How fast does B observe A? So if you're in car B and you look in your rearview mirror, you're going to see that car A is catching up with you at 5 miles per hour. Basically, you're just taking the difference of these two velocities. And you're also going to observe C coming at you at minus 30 miles per hour. You're driving down the road, you're going this way. C looks like now it's moving 30 miles an hour towards you, towards the south. That's what this minus represents. So now car A collides with B. Let's assume their masses are equal. We have a totally inelastic collision. This makes our math a lot easier. What are the change in velocities that C observes? So let's go ahead and do this problem right here. So one thing that we know about collisions is the final momentum is equal to the initial momentum. So C observes that MA plus VB initial MB, and this is a totally inelastic collision, so I can stick these two guys together, and they're going to move away at some velocity. So that final velocity, since all these m's are equal, they're all going to cancel out, and I'm just going to get a 2 over here, because this is 1 plus 1, that's 2. This side is just m's. So I'm going to get VA initial plus VB initial divided by 2. So what I'm going to get is 32.5 miles per hour. And this is pretty much what you would expect. It's just going to average what's going on. Since the masses are the same, that will make the momentum be conserved. So car C observes the wreck, right? So here's C. C's minding their own business, and A and B have an accident. And they go sliding away at 32.5 miles per hour. However, let's now consider what happens if B is our observer. So if B is the observer, now VB initial is 0. And VA initial is at 5 miles per hour. So it's still going to be a totally inelastic collision, so this is going to look pretty much the same. So here we have MA VA initial is going to be equal to, now B looks like it's at rest, so we lose that term. MA plus MB V final. However, in this case, we get that V final is going to be 2.5 miles per hour. So this is when C is the observer, this is when B observes. So let's consider the change of velocities that we have. So delta VB final is going to be 32.5 miles per hour minus 30. So that's going to be 2.5 miles per hour. Delta VA is also going to be 2.5, but it's going to be minus 2.5. It was going 35 miles per hour, and now it's going 32.5. So these delta V's are equal and opposite. Since their masses are equal, this works out. So in the case where B is the observer, delta VB is going to be final, so that's 2.5 minus initial, so that's 2.5 miles per hour. Delta VA is going to be a minus 2.5 miles per hour. So what we have here is that our delta V's, or in other words, our delta P's, stay the same regardless of which frame that we're in. And that's where all the physics comes into play. So when you observe something from different reference frames, like either a rest frame or a moving frame, the collision may look different. In one case, you had one car moving at 30 miles an hour. In another case, a car is only moving at 2.5 miles an hour. And it may look different, but the physics of what's going on will remain the same, regardless of which reference frame that we're in. Now, here's another special point here, is that in all these cases about reference frames, what we're really talking about are inertial reference frames. And this is really just a fancy way of saying you got to be moving at a constant speed if I'm going to consider you to be an inertial reference frame. So if your reference frame is accelerating, physics will not look the same as if you were in an inertial reference frame. And we'll talk more about that in the next chapter. Center of mass. Center of mass is a topic I hope you'll find a little intuitive. In simple terms, the center of mass is just a point. Let's consider this triangle here. And now this triangle is going to be thrown into the air and follow some trajectory. We were able to work out what this trajectory looks like. We know from kinematics we're going to get something like the initial t plus 1/2 at squared, and these sort of equations to be able to describe the motion that's going on. But what we assumed was that this triangle is just a point mass, or this person is just a point mass accelerating and having some velocity. But that point at which we're kind of idealizing our body around is the center of mass. And so this is a point at which basically we can pretend that all the mass of that object is at that point. We can have a crazy geometry like this, and if you jump through the air, your center of mass will also follow a similar trajectory. Now you can jump in the air and wave your hands around, and so certainly your hands don't follow the same trajectory as this. What will happen is that your center of mass will still follow the trajectory described by these simple kinematic equations. So then how can we find the center of mass of something? So let's look at a few examples. So one was this triangle, and I ask you to find the center of mass. And it's pretty easy just to put your finger at this geometric center here. But what if we had a more interesting shape? Let's do another simple one. So let's say that we had a golf ball on a tee. The center of mass is going to be right in the center of that golf ball. So let's consider a little bit more complicated one. Let's assume that we had some baton or dumbbell or something like this. Where would the center of mass of this dumbbell be? Well, we could think about this dumbbell and where would we want to balance it at? So the center of mass, sometimes I'll write it as COM. We could think of this as a balance point. And in some ways, this balance point is a lot more specific than just talking about picture frames, because you could hang a picture frame just by, using one nail up here, and then your picture frame will remain nice and level. But this is a balance point for all directions of the thing. So we know that if you really wanted to balance this picture frame, you need to balance it this way and this way. The center of mass will be the very center of this picture frame. You could turn it any direction and the picture frame will be just happy sitting there. So in the case of the dumbbell, where would we want to balance it at? Well, right in the middle again. So the center of mass of this thing is right in the middle. We know it easily balances at that point. If we threw it in the air, we could kind of see that the thing would spin around this point right here. So what if we consider something a little bit more confusing, more complicated of a shape? Like maybe a tennis racket or a baseball bat or something like this. Where would the center mass of this racket be at? So you could try to balance it on your finger this way or that way or something. We'll probably find out that it's a little closer to this handle than to the racket part. So it's not just talking about where's the center of this object. It has to do with how the mass is distributed in the object. So let's consider a more complicated baton. In this case, we're going to have one with a mass equal to 1, and then another with a mass equal to 2. So another way you could think of this is kids on a seesaw. So maybe that will help you conceptualize what's going on here. So where would you want to balance this baton at? Closer to the mass that's heavier, so somewhere over here. So how can we figure out mathematically where is this point instead of just testing out a bunch of cases until we finally got it right? One thing is that we need to kind of label our coordinate system. Let this be x. Let's put them right on the x-axis, and then let this ball be at x equals 0. So the center of mass is going to be the sum of all of your masses times their position divided by the total mass of the system. Now don't get confused here. This sum of mi can't cancel out with the sum of this mi, because inside this sum there's this product with the positions. So it doesn't just cancel out. So sum of each of our mass, so this one is going to be mass 2 times the length of our baton plus this mass, just 1 times 0, divided by the total sum of our mass. So we can't forget this guy. So 2 plus 1. And here we're going to end up with 2L over 3, or 2/3 L. So going back to our mute swan. So here the swan flies over this nice quiet lake. We could say that the center of mass of the swan has to be somewhere back here. The wings are supporting its weight. We know that gravity is trying to pull it down, but the wings keep holding it up. And so one of the reasons why it has to stretch its neck out like this is in order to help the swan balance about this point. So you can look at the whole swan, and we're going to kind of idealize it like we did that baton. We're going to dissect it into little chunks. So where would the center mass of this head neck part be? Somewhere in the middle. And then where would the center of mass of this piece be? Well, somewhere in the middle of it. So maybe somewhere over here. And then what we're doing is we're summing up these two positions that we've kind of idealized our system to be at, and then taking that sum again. So just to let you see it again, sum of mass I, xi, all over sum of the masses. Total sum of the masses is our center of mass. So here, the center of mass is a lot closer to where the body's center of mass is, because there's a lot more mass in the body than in the neck, although the neck does help orient the bird. All right, for our final example, we're going to be looking at where's the center mass of this open box. So if the box had a lid, it'd be pretty easy to point out, well, we can just use symmetry and argue that the center mass of the box is going to be in the center. So, but this case, we kind of don't have complete symmetry here. We have an open box. So if we're looking down at the box, we can use symmetry again to argue that center mass is going to be at x equals 0, y equals 0. We know that has to be somewhere along this axis. So we're going to call that axis z. But what we don't know is where is the center mass going to be along z right now? Because if we had the lid, that'd be easy. It'd just be the length of one of these sides over 2. But we don't have that lid to help balance things out. So we're going to have to work this out. So we know that the center mass is going to be mi zi over the sum of our masses. So we're just going to let each of our mass of each of the sides all be the same. So that's just 1. So now, where are the center of each of these blocks? Because what we can do, instead of doing some integral, we can say, well, this wall right here, it's pretty easy to point out where its center mass is. And it's right there, right at L over 2. So I've got 1, 2, 3, 4 of these guys that all have a center mass at L over 2. But I can't forget that there's also a bottom here that's at 0. So I'm going to just write all these down. So I'm going to just bring those m's out. And so I'm going to have L over 2 plus L over 2 plus L over 2 plus L over 2 plus 0. So 4 sides in the bottom. All divided by 1, 2, 3, 4, 5 m. So those masses are going to go away. And so I'm going to be left with 4 L over 2 all over 5. I can simplify that down to be 2/5 L. So our center of mass is at x equals 0, y equals 0, z equals 2/5 L.